Okay, so far we've covered the basics of how a cow works from a gastrointestinal standpoint in terms of just the basic fundamentals, and then we talked about carbohydrates. Now we're going to talk about protein. And basically what we want to get out of this is how the animal and how the microbes work together to process protein and then absorb it and then deposit it in muscle. So we'll go ahead and label these things real quick. We have the mouth, the rumen, the abomasum, the small eye, the large eye, the pancreas, the liver, and the gallbladder. Okay, we're going to add a new muscle type, or we're going to add another new tissue type, and that's going to be our slowly dying red marker will be muscle. Okay, because when we look at beef cattle production systems, and if you were like in a dairy or had a lactating cow or a gestating cow, you could write conceptus or you could write milk. But our goal is going to be able to get amino acids or protein from the diet and get it deposited in some usable or sellable product. Okay, so just briefly, proteins are made up of amino acids. Okay, and amino acids are kind of like the building block of tissues, so you're going to use amino acids to build tissues. They're really important in reactions and enzymes, and basically you exist because of the activity of 20 amino acids, 10 of which are essential. But we don't need to get into a tremendous amount of detail about amino acids to understand the cow. The one thing we do need to understand is that all of the amino acids contain nitrogen in the form of ammonia. And so we need to make sure that we know that amino acids and protein contain nitrogen in the form of ammonia. So we have our cow, and our cow comes to the bunk or is out grazing, and she consumes intake protein. And that goes into the rumen, and it is fractionated into two fractions. Okay, and this is important that we get the words right. The first fraction is degradable intake protein, so DIP. And the second fraction is undegradable intake protein. Okay, and so degradable intake protein, okay, DIP, degradable intake protein, can be utilized by microbes. So what that means is the protozoa, the bacteria, and the fungi can use degradable intake protein as a source of nitrogen or amino acids. Okay, UIP is not utilized by microbes. And sometimes if you go to the feed store or listen to people talk about it, you might hear this referred to as escape or bypass protein. Okay? And so what happens to undegradable intake protein is it bypasses or escapes the rumen. Escape is a better word than bypass, and goes to the abomasum. Degradable intake protein is different in that it moves through a series of cycles, so we can have protein, and that protein can become an amino acid, which is used to synthesize microbial crude protein, which we've learned about before. MCP equals microbial crude protein. or those amino acids can be degraded to ammonia plus a carbon skeleton. Okay, and these go both ways. So a feed protein can be degraded to amino acids, and then it can be degraded to ammonia, and then it can be resynthesized back into amino acids and become microbial crude protein. Okay, or we can feed ammonia, and when we feed ammonia, we normally talk about NPN, which is non-protein nitrogen. So if you use some liquid feeds or some molasses type blocks, those contain non-protein nitrogen frequently, and non-protein nitrogen includes stuff like urea, ammonium salts, biuret, etc. Okay, and so we can actually have ammonia come from the diet directly. Okay, the other thing that can happen with ammonia is the ammonia can be absorbed directly out of the rumen. Okay, and if that ammonia is absorbed out of the rumen, it goes to the liver. Okay, and in the liver we make urea, and that urea can be recycled back to the gastrointestinal tract. And where we really care about this recycling is to the rumen, and that urea becomes ammonia, and that ammonia can feed into this ammonia. And in that way, ruminants can conserve nitrogen, and it allows them to live on a lot lower protein diet than non-ruminants. So this is nitrogen recycling. If you ever hear anyone talk about it, unlikely, but someone may talk about it, and if they do, you know what it is. You're taking ammonia, absorbing it, detoxifying it to urea, and recycling it back to the rumen. Okay? The other thing that the microbes need to accomplish this synthesis of microbial crude protein is energy. Okay? So we require a source of nitrogen, and we require a source of energy and some carbon skeletons, and they can synthesize microbial crude protein. Okay, and the energy comes from the fermentation of the carbohydrates we talked about on the previous figure. Okay, so that's kind of what's required to synthesize microbial crude protein. The microbial crude protein flows out and goes to the abomasum. Okay, and once we get here, we talked about on the first drawing, we have the addition of hydrochloric acid by the animal, and we have the addition of pepsin. Pepsin's not how it's secreted, but that's what we're going to call it for today. And so those are secreted, and those two, HCl and pepsin, start digestion of protein. Okay, once we basically get to here, or they're treated the same, so UIP and MCP are treated the same, and the enzymes and the acid are going to work on them. Okay, and from the pancreas, we have the addition of buffer. And we also have that addition of buffer from the small intestine. Also from the pancreas, we have proteolytic enzymes. And from the small intestine, we have the addition of proteolytic enzymes. Okay, so these proteolytic enzymes are basically going to work on the MCP and the UIP to break it down. And what we're going to end up with are amino acids and di and tri dipeptides. And a dipeptide equals 2 amino acids joined. And the tripeptide, as most of you can guess, equals 3 amino acids joined. Okay, and those are absorbed by the enterocyte, or the cells in the small intestine. And inside, they become just amino acids. And those amino acids go to the liver. Okay, in the large intestine, we can again have the synthesis of microbial crude protein and all that that entails. We can also have the production of VFAs, but that's more related to carbohydrates. But this microbial crude protein that's synthesized in the large intestine is excreted in the feces. So this is a big difference between your hindgut fermenters like a horse or a rabbit or an elephant and a ruminant, in that by having the rumen or the fermentation in front of the small intestine, they get to take advantage of microbial crude protein production and not just excrete it in the feces. Okay, one concept that we need to make sure we know is that ruminants can take a low quality protein and through microbial activity, sorry, it's getting messy. Through microbial activity, they produce a medium quality protein. Okay, so this is a good thing. We like this because they're taking feedstuffs that we can't utilize or that have a poor amino acid profile that wouldn't meet our requirements, and through the actions of the microbes, they're making a medium quality protein. On the flip side, they can take a high quality protein and convert it to a medium quality protein. So as a result, we don't typically feed ruminants high quality proteins because we're really not taking advantage of their ability to increase protein quality. And these typically tend to be more expensive, okay? Whereas low quality proteins tend to be cheap, and low quality protein can include things like NPN, which isn't even really protein at all. Okay? So briefly, the amino acids go to the liver and they're released to the body. And what we really like to have occur is them to go to the muscle or whatever productive unit we're doing and add to that. Okay, if you have a cow and she's grazing dormant forage, we can actually have the mobilization of amino acids from the muscle, and those go back to the liver and they can use them as a source of energy. Okay. One final thing we need to capture is any excess amino acids, any excess nitrogen ends up as urea in the liver, and if it's not recycled back to the rumen or the gastrointestinal tract, it is excreted in the urine. Okay, so nitrogen, excess nitrogen gets excreted in the urine. So the real big take-home message is that for this to work effectively and for carbohydrates to be digested effectively, we need to provide nitrogen that meets the ruminal microbe requirements for nitrogen so they can effectively ferment structural carbohydrates and non-structural carbohydrates into energy and use those to synthesize microbial crude protein.